kilonova, macronova, afterglows, maybe getting on within a day is good enough. But there are some other ideas for sort of hour-long things. And so I guess the question is, back to this question of how rapidly we could get LSST onto one of these events. So maybe I'll just say one thing. One is that if you have free neutrons in the outer layers of the ejecta, the neutrons have a fairly short decay timescale, 15 minutes, so you can superheat the outer layers, and you might get something that's quite luminous and in the optical for, say, a few hours after the merger. I think Svi has an idea. I'll let him say in a second, but so maybe I'll let Svi say something quickly.
Well, the other idea is, I briefly mentioned it in my talk, is that the jet goes through the ejecta, it hits the ejecta and produces a cocoon, and this cocoon will have about 10 to the 50 ergs, and then as it breaks out from the ejecta, you see, it's just like in a supernova. You see this hot material cooling. This is the first emission of the supernova. It's like the cooling phase of the supernova. It's the first phase of the supernova. And this gives a signal which is of the order of a 20-second magnitude, 20-second magnitude for a 200 megaparsec for a duration of about 1 hour. So then later on, the macronova signal picks up. But you have 1 hour with a bright, and this is very blue signal. The signal is very blue. It's actually peaks in the UV, but it is very blue signal. So this is a very bright one, but short one.
How fast is the material coming out? Will it be quasi-isotropic, the signal, or is it moving relatively quickly?
It spills out. It is getting out at about 0.1 C, so it spills out and it becomes quasi-isotropic. So once it gets out, it will spread out, and you'll see it from all directions. So it's an isotropic signal, quite strong, fast, and weak.
That's basically identically what the neutron occurs, so we can argue if we discover one.
So, yeah. No, but it's reassuring because there are two different mechanisms that will give you a strong signal. Then we can argue about the same.
I have a question related to that. I think it's the plot you showed pretty early in your talk, and I couldn't read the x-axis, but it looked like a pretty broad curve over a fairly short time. Like, when does it actually cross the threshold where LSST could observe it? Like, on the rise up? Like, could you see it within 15 minutes? Does it get that, or is it very sharp? I couldn't remember. You know what I'm asking? Like, you said it peaked in an hour, but the question is, when does it become visible on the rise? And
it's probably rising is like t squared up to an hour. So
okay.
Something like
and the question is it any different than what your model would be? Is there anything you learned from observing earlier? Is what I'm asking. Because that would be matter for
unclear presently.
If you really want to go.
Well, this depends on which band you're looking. For the signal that I'm talking, and I guess it will be the same for the signal that Brian's talking. The blue, if you're more in the blue, you should look earlier.
So my question is how blue? That is to say, would we see it only in the G filter and not the R filter? How deep?
It's a black box.
Oh,
it's a black box.
See it in both.
You should see, yeah, definitely.
So you should definitely see it in all bands. But we were just calculating the G spectrum.
So that's, I guess, the question of the slew time and latency. Basically, it's a combination. If LIGO latency plus LSST slew time can be less than an hour, that would be interesting. We could talk more about it.
Yeah, but the question of whether it's an hour or whether it's 8 minutes or something, that may affect how we do things. So yeah, that's.
But if the rate limiting thing is LSST, it sounds like it's not the LSST slewing time. It's not the rate limiting.
We can slew in less than 10 seconds. Problem is, it might be noon.
That's that problem too. I recommend selecting based on that.
Yeah.
What we can do is just turn off all of the LIGO detectors while it's daytime.
Start somewhere.
All right, let Andrew
Well, it's daytime and LSST because
Here,
Oh, it's up there.
over there. Yeah. Okay. Oh, I was going to manipulate it, but anyway, let me just, in a sense, advertise the Afterglow library. And what this is a way to compute the light curve as a function of explosion energy, frequency, circumburst density, but very importantly, the observer angle as well. So if there's a relativistic jet propagating into the ISM, it'll drive a strong relativistic blast wave, which is beams radiation. But if an observer is some angle away, they won't see the burst at first, and it'll come up later. And so SVI, before, when Fei showed densities at 10 to the minus 3, but you can actually just go in and change this to 1. And this will show what how the light curves change as a function of this density and also observer angle.
Can I change it?
Yeah, sure, you can change it to 10 to the minus 3, which is what I'm going to show you. Then hit submit. And so, yeah, and so...
Order of
yeah.
magnitude in flux.
Yeah.
Yeah.
Yeah,
Okay.
yeah.
It's order of magnitude in flux.
Right, and it's also
order
shorter.
of magnitude in.
Right. And the other nice thing about this, and this is all, you can download these light curves, is you can also change, this is R-band, but you can also go to X-ray or radio as well, and plot light curves as well. And then if you go down a little bit further, you can download it. You can just click here, maybe. Yeah. And it gives you all the information about the radiation model, and also you can download the data. And so you can generate these at X-ray, radio, optical, whatever you want, or even low frequency radio. Change the density and notice how the timescales change. And you can also change the observer angle. So you can be either completely off axis or in the cone of the jet, but near the edge of the jet where most observers will be. Also 45 degrees or 90 degrees. And then you can make these kinds of plots. Yeah.
So you also had some code to like actually compute multiband,
Yeah.
SEDs from using your simulations and a bunch of scaling relations. So
Right.
what is where is that code available now?
Yes, it's, if you go up here to code, it's supposed to be there very soon. Let me see if it is. So you go to the code here. Right, sphere fit. So this is going to be replaced by scale fit, which is in preparation. So that should be, I think this year, Hendrik van Rieten is leading this, and this should be in the next few months, I believe.
Okay.
So this is the new technology of touch screen. Which
Yes, exactly. but anyway, feel free to poke around if you like. This is all free and publicly available, and I think it should be very useful. Yeah.
I'll just add the box fit, the scale fit code does this, computes these afterglows with these scaling relations based on this sort of table of templates, and it does it very, very quickly, but it's all based on the box fit code, which is also available. So if you have the time to run things yourself and you want to compile all the source code, you can do that, and you can do it for any frequency band you want.
Right, and BoxFit just takes the simulation, so it's relativistic hydrodynamics, and takes all the data, puts it into a time series, so you can download that, and then you can add any radiation model that you'd like. So that's BoxFit. And then ScaleFit can be used in MCMC codes because it uses scaling relations for the radiation to produce light curves in about a millisecond. So you can go over full parameter range and explosion energy, density, and observer angle, and fit the shape of those light curves and multiband. Okay, that's all I want to say.
Very exciting, thank you. Kennedy went up?
Yeah.
Did we have a question?
So the parameters that go into these, how can we, or how are they interpolated is the first question. Because I'm sure you're not wanting to do hydrodynamics
Right, it
everywhere.
turns out for synchrotron radiation, the spectrum is very simple. There are just a few break frequencies and an overall scaling of the radiation. And so because there are power laws in between those frequencies, all we have to do is tabulate those frequencies from the simulation, and then we can generate any energy, any explosion, any density. It's completely scales.
And the second question about this is, do we know what the population is going to be in terms of those parameters?
Well, yeah, I mean, from short GRBs in general, we have ideas of what the opening angle of the jets are and what the energies are, and what the density obviously is. If you really want to bump up the luminosity, you just assume there's a high enough density, and that you can do that here. But yeah, sorry. So yeah, we know how it scales with density, energy, and opening angle of the jet. Yeah.
So if we want to use the code, for example, generate a gallery of images, is it possible to also extract information about how many exposures from LSSD would be necessary to recreate one of these live codes?
Sorry, say it again a little louder.
So if you wanted to try to nail down one of these live codes using LSSD data, can you provide information about how many seconds of observations or exposures would be needed for that?
Yeah, so Wenfei was getting at, yeah, so you can just take this, you can generate this light curve, given what your telescope can do, then you know what the flux is in this case, in the Lagrangian. So yeah, you can make those calculations. You have to do that yourself. We'll just give you the light curve and then you can, yeah.
Anti-limited measure.
Yeah, so Andrew already talked about this. So I just want to focus on the title is not, yeah.
That's something else, right?
Already, Wenfei and David already told you about kilonova and macronova. So I want to just focus on the open theoretical issues on this modeling. So roughly speaking, the luminosity, peak luminosity of peak luminosity of kilonova, macronova can be estimated something like this. So you need the total amount of ejecta mass, which is fully composed of radioactive material, times the radioactive power per unit mass at the peak time. And then you have to multiply some thermalization efficiency of their decay. For example, neutrino just completely carried energy away. So this is some correction. And here the peak time scale depends on, we think, something like this. So which significantly, the most important factor here is the opacity of our cross elements. So I want to focus on these three issues. So first of all, so this is David already talked about. So we don't know really about what is dynamical ejecta, what is a wind ejecta, and mass is quite uncertain. So basically, the main uncertainty to predict the mass of the ejecta is just we don't know the neutron star equation state. So, but as David already told us, and then maybe Satya will talk about, the LIGO will be able to determine the neutron star equation state, then the prediction may be much better. And also the disk wind composition, like Brian already worked about. So it's still it's unclear that how much material is ejected from the disk. It's maybe, so far the calculation have been done with alpha viscosity, but maybe the magnetic field and MRIs change this result. So the second question is still nuclear physics. We don't know really much. So for example, these are actually energy source of the radioactive heating of macron. So alpha, beta, gamma, neutrino, and nuclear fission. So just this is a rough estimate how much energy deposited per decay. So for example, alpha deposits 5 MeV, and beta, gamma 1 MeV, and the fission, one fission release is like 100 MeV. But the efficiency of these energies deposited into the ejecta is just, for example, neutrino doesn't deposit energy at all. And roughly half of the alpha, beta deposited in this ejecta. But so far, more or less we know beta, gamma decays, but the main uncertainty is fission here. This contribution is from very, very heavy nuclei, and they should be in ejecta just soon after the merger, but we don't know exactly the lifetime and of these super heavy nuclei. So potentially this fission can provide more energy, but still we don't know much about this fission.
Why do you say the gamma ray efficiency is less than 10%? Is it because the gammas are escaping without interacting? Is it that transparent?
Yes, because the Compton scattering, actually this is the problem linked to the problem, the next issue of the optical opacity in the optical is much larger than Compton scattering cross section. That means gamma rays escapes faster than earlier than optical.
So what about a gamma ray signature?
Right,
Yeah,
gamma rays,
exactly.
we expect some gamma ray signatures. It's very hard to detect, like few megaparsec, then we can detect.
But obviously it depends on the instrument, right?
Yes, we assume.
We'll see
like-
many nickel 56 decays from 1A supernova.
Right. I mean, this, Peter and I were at a meeting earlier this week where we were discussing next generation MEV gamma ray instruments. And the predictions there are that we would get handfuls of SM1As per year, and we wondered whether making observations of the nuclear lines here was something that was potentially feasible. And
Yeah, I can show you
the action
the
item
specs
from the
from-
end of that is that
yeah.
we needed to ask more people.
Yeah,
And here you all are. So,
Yeah, and basically the typical energy is 1 MeV, and you have some
right.
somewhat broad because of Doppler broadening and something.
It's like these are like a tenth amount of radioactive material,
Yeah,
and they're
it's-
100 times as rare, so you can kind of figure out. So it might be really hard, but you probably have to see
Yeah.
thousands.
It is
1A.
much less energetic than a type 1A.
Yes, and
So,
we
right.
understood that. We just didn't know whether it was completely hopeless or.
If while building the detector, you also build the Newton star merger 5 megaparsec from us.
Perfect. We'll get right onto it, Steve.
Yes. The last issue is opacity. So actually, the number of atomic lines in these heavy elements is huge. Like one, for example, lanthanoid has 10 to the 8 lines. So there is huge opacity from this atomic transition. So for example, this is opacity as a function of photon energy. So this black one shows some line expansion opacity. So because like opacity at 1 MeV to 10 MeV, which is huge. So this causes huge opacity in optical band, and the ejector temperature goes down, the optical depth opacity getting smaller, and in the end you will see the signature. But still there is some contradiction.
EV or what are the units on the bottom? Did you
It's
see?
electron volt, 1 eV and 0.1. So less than 1 electron volt, the opacity tend to decreasing. But still there are two different ways to calculate the opacity. So one is the Sobolev expansion opacity, and then another recently this paper suggests the other method. And this increases opacity around here, the low energy photons, like something black to red. So still, in that case, the opacity around the near infrared increases by 100. So in this case, it's kilonova is much fainter. So still, but this one maybe theoretically should be addressed soon. So it's important issue.
Thanks. Yeah, I just wanted to briefly mention another possibility of maybe generating a potentially optically bright electromagnetic counterpart. And that goes back to some previous ideas by Brian and also others, and essentially applies to the case in which we have a binary neutron star merger that produces a long-lived neutron star remnant, and there's both theoretical and observational evidence that actually maybe even the majority of binary neutron star mergers might produce such a long-lived object. So in this case, we have this binary neutron star merger system forming this long-lived neutron star, and then as David has already discussed earlier this morning, we have all sorts of ejecta that pollute the environment with a lot of baryonic material. There's the early dynamical ejecta from tidal tails. There's more thermally produced ejecta by the contact interfaces of the binary. So these early dynamic ejecta, but then later on they can be on timescales of hundreds of milliseconds up to a second. There can be other types of ejecta from post-merger accretion disk or from the remnant object itself. So there's a lot of baryonic pollution surrounding this merger site, and as these baryonic ejecta processes stop at some point, and the unbound ejector is moving away from the merger site. There's sort of a cavity that is formed around the merger site. And the density drops, and so then the strongly magnetized neutron star will start to launch a pulsar wind and will eventually fill this void with what's called a pulsar wind nebula. So the basic idea here is basically that we have some ejector that additional to the nuclear binding energy that is released by the R process and which heats up the material. You also have an additional power source, which in this case is a magnetar. So you essentially can tap the rotational energy of a magnetar and have an additional energy reservoir that can heat up the material and lead to thermal and also non-thermal radiation. Essentially, there's a lot of unknown physics still, and we're working on more detailed models for this, but early, say, estimates suggest that you can actually get fairly bright signals, so at least the volumetric luminosity is very high, orders of 10 to the 45 to 10 to the 6 ergs per second or something. The problem still remains to see like what the opacities are and to take more detailed physics into account to predict like what would actually be the, for example, the luminosity in the optical. But so also Brian has some early predictions in his kilonova handbook that on like simple models that already suggest that you can actually get like 2 orders of magnitude at least in maybe in the optical, so brighter than a typical kilonova signal. And this would also be at earlier times, so maybe on timescales of typically minutes to hours or so, a little bit earlier than the typical R process heating. But there still needs to be more theoretical work to be done on predicting in a more precise way what the expected signal would be in terms of optical luminosity.
The next is Polka, but he's not.
I guess, running late. So, is that, do we lose afterglow?
Well, it's 3, but...
I discussed it. No need to.
Sorry.
But this is just an indication of, this is the G magnitude. And you can see the rise, and the time schedule is about 1 hour.
Oh no. This should be another one.
This one.
I mean, we can also just open it for discussion. I think that's probably.
Yeah. I can probably just talk in words if my slides are not on there. That's the last slides on this in this
I think
video.
you skipped some slides.
Yeah, so
I saw it earlier on yours, Kent. I'm confused.
these are all. My slide just had a cartoon anyway. I can speak in words. That's fine. Just not right. Sure. So yeah, I'll just say a couple of things briefly about progenitor channels for making black hole binaries. As most people here know, it's currently not clear which astrophysical channels source the black hole mergers that LIGO has already seen, and indeed it's also not clear which astrophysical channel produces the majority of the black hole mergers in the universe. There are 2 sort of classical progenitor scenarios which are commonly modeled and debated. There's the evolution of isolated field binaries that may or may not go through a common envelope phase of evolution. And there's also the dynamical assembly of binaries in 2+1 encounters in dense stellar systems like globular clusters. But there are a number of more exotic scenarios for usually dynamically assembling a black hole binary that can merge in the universe, which have not received quite as much attention. And I was asked to just speak for a couple of minutes on one relatively novel one that was proposed by 2 different groups at Columbia last year. One was led by myself, the other was led by Imre, but the ideas are fairly similar. And they have to do with the dynamically rich environment of the gaseous accretion disks surrounding supermassive black holes in the small fraction of galaxies which have active galactic nuclei. So relatively wide binaries of stellar mass black holes that find themselves in these gaseous accretion disks can be externally induced to merger, even if their orbital separation, their semi-major axis, is much larger, potentially orders of magnitude larger than the critical semi-major axis that will merge due to gravitational wave emission alone in a Hubble time. And there are a couple of different mechanisms that can speed this merger process along. The clearest one is just hydrodynamic interactions with the circumbinary mini-disk that forms around the stellar mass black hole binary as it travels through the AGN accretion disk. There are a couple of different ways of getting stellar mass black hole binaries into this sort of environment in the first place. First off, it's been known for a long time that the outskirts of AGN accretion disks are tomb ray unstable, which is to say unstable to gravitational fragmentation. And there are a number of reasons to think that episodes of gaseous inflow in galactic nuclei should produce substantial amounts of star formation. We see an echo of that in our own galactic center, where there's a massive disk of young O and B stars on subparsec scales. Furthermore, pre-existing stellar mass black hole binaries in the center of a galaxy can just be captured into a temporary gaseous accretion disk due to hydrodynamical drag as they're passing through the disk. The details of this process still have a lot of uncertainties. Imre and I each tried to estimate rates, and I think probably a few per cubic gigaparsec per year is what we get fiducially, but with significant uncertainties in both directions, up and down. The reason I think it's very interesting to think about this scenario is that it points to a possible more indirect way of identifying a source channel electromagnetically for a gravitational wave signal. And Imre, were you going to talk about this, or
no? I was going to let you. Yeah.
Okay. Well, in a very nice follow-up paper that Imre led this year, we did a simple Bayesian analysis to ask if X fraction of all the observed black hole gravitational wave signals come from a source channel associated with a rare subpopulation of galaxies, how many gravitational wave detections would LIGO need before its gravitational wave error volumes alone, even without any electromagnetic counterparts, could point to that percentage, that X percentage of black hole mergers coming from that more exotic channel. So under the assumption that the strong AGN that produce externally induced black hole mergers constitute about 1% of the total galaxy population in a volumetric sense, Imre estimated that roughly 70 LIGO detections without any electromagnetic counterparts would be necessary before you could say that AGN were statistically overrepresented in those 70 advanced LIGO error volumes drawn from the estimates of Chen and Holtz. So even without electromagnetic counterparts, if you think that a large fraction or even a smaller fraction of black hole mergers are originating in a rare subpopulation of galaxies, it may be possible indirectly to test that hypothesis just by correlating LIGO error volumes with galaxy catalogs.
What error volume did you assume for LIGO for that statement? 70?
Per estimates. Sorry? So, well, there's a distribution, right? So you get the most contribution from the best localized signals, right? So it's all about, focusing on a few events that are very well localized, maybe more beneficial than the majority of the events, essentially. So what was really good about Shinju's work is to show that we can really get more science out of a few events that are well done, as opposed to a larger population, essentially.
But this was assuming the 3 detectors. With
3 detectors, exactly. So with 2, it would be very hard to do anything like that. Yeah. So you need 3 detectors. So Virgo needs to get it up together. Tony?
This is inside of what distance?
Inside of what distance? So this is for black holes. So essentially, you can go out to redshift of 0.1, 0.2-ish.
So there are all sorts of types of galaxies in that volume. How am I going to tell the difference?
So you can localize some of these events. She knows better, but say 10 to the 3-4 cubic megaparsecs. So it's some of them can be very well localized, and you have to find what galaxies are in there, and you have to say that, okay, well, if AGN are overrepresented, then there can be a causal connection. Otherwise, there's nothing like that.
Very efficient at discovering the AGN in each of
Yeah,
these
you need to know.
areas.
You need to know the
Yeah.
galaxy, exactly. So it's not enough to. Yeah.
Since we diverge to this topic of progenitors of black hole mergers, which is not exactly LSST, I just want to remark about recent work that Kenta and we have done, and also the group of Kushner, Weizmann. From the observation of the spins of the black hole, one can infer quite a lot about the progenitors. And in fact, the standard scenario of isolated would predict highly rotating black holes with spins aligned with the orbital spins. And so far in the 3 detections which were reported in 01, there was not a single one which was observed like this. So, this is not enough to question this model, but definitely with a couple of more detections in 02, if high spins like this are not detected, this will rule out the standard scenario.
Can you quantify high? Can you quantify high spins?
One. A over N is 1.
But it really needs to be that high, because I mean, GW15126 was
Excuse me?
above, GW151226 was above 0.2 kilowatt.
No, 0.2 is
Too low.
Is too low, much too low. Yeah. All the observed ones are much too low.
So to bring this back to LSST, have you thought about precursors? Because Jeff Ryan, who's here, has done some very nice work on binary black hole accretion. He finds that the mini disks around each black hole should be very bright.
Yeah, I think that's a super interesting future direction for thinking about this AGN channel, because it's one of the only scenarios where you get an interesting number of black hole mergers in a very gas-rich environment. The black holes will have these mini disks around them at the time of merger. The problem is that there will be an AGN in the background, so you would have to come up with some kind of electromagnetic signal, maybe a jet that's launched from the last stages of the mini disk evolution that could outshine the background AGN.
Or he finds time variability in the accretion, so maybe there's a...
Yeah, we should talk about that more during the lunch break. That we haven't done any calculations.
Like one last point, maybe.
I have a question, unrelated question, but since we mentioned binary black holes that LIGO has observed a couple of times, I really wonder if there is any evidence that binary black holes might actually form differently compared to binary neutron stars or neutron star black holes, and whether what we are observing has any relevance to EM follow-up at all. I mean, does the panel think that we can already learn something about
This
EM
is just
observation?
what I said, that the low spins are not sufficient to rule out any model, but they begin to question the standard isolated binary which evolves. So already now, these 3 observations make it unpleasant. Tension, what is tension?
Yeah, tension.
Yeah, and also for neutron star black hole mergers, so we need a large spin for large mass ejection. So current LIGO detection is not really happy for us.
Large spin and small black hole mass, so
Yeah, that's
doubly unfavorable.
We were actually at a conference in Pasadena last summer, I think, and we were discussing. I think all the groups are actually feeling a little hot water about the spins. I think it's actually in almost all the scenarios that have been proposed, you should expect fairly rapid high spins.
Yeah, but for dynamical mergers, you don't need to be aligned.
Yes,
right?
for
So we're
dynamical
only
mergers, but
constrained
there will be
aligned.
some, yes.
Yeah. So far, it's all consistent with just a random direction, even high spin.
By dynamical merger, you mean the kind that we were just speaking about?
Of any kind.
Dynamical,
Dynamical, not necessarily.
in what sense? I mean, it's always dynamical, but with material around that, or what?
The usual dynamical assembly scenario is that you have a dense globular cluster environment where single black holes can swap into pre-existing binaries just through sort of chaotic 2+1 encounters. So that's the usual mechanism to produce a binary with randomly distributed spin vectors.
But and then they align, or what?
No, they will not.
No alignment.
Then there's no alignment. But in the usual scenario.
But when you say usual,
they are locked.
I'm sorry.
The usual scenario would be the evolution of a binary of massive O stars just isolated in the field, which both become black holes, but because there's a mass transfer episode, the spins are able to align with each other.
Considered usual.
Well, not anymore, right?
I wouldn't take it as canonical.
Yeah. Okay, I think we have to conclude and go for lunch. So we're a little late in time, so maybe let's make the next session start at like